Gokul, I think you can start.
Yeah. So hello guys, welcome to the session 7 of the summer school conducted by the Analytics Club and the CVI Club. I'm Gokul from CS21. I'm a coordinator of the Analytics Club. I'll be covering regularization today, and Ashish, a coordinator of CVI Club, will be covering Opencv, and then Nived, another coordinator from the Analytics Club, would be covering CNN, and he'll be doing an implementation as well. I'll try to share my screen now, so let me know if it's visible. Archish, is it fine? Is it visible?
Yeah, it's visible. Maybe you can go to full screen. Yeah, it's fine.
Yeah. Let's dive right in. So, what is regularization? So, regularization is a technique which we use to minimize overfitting. So, like basically, why was it thought of, right? When like in the 1990s or something, when the machine learning models were becoming famous, when machine learning was taking off, people noticed a common issue, right? So what that issue was that most models tend to overfit. Like they used to perform well in the training, in the proper training data set, but if you manually add some external noise to the training data set, they used to like crazily overfit and used to give horrible results. So people wanted to address this issue, and that's why regularization was thought of, right? So here it's a simple graphs explaining underfitting, appropriate fitting, and overfitting. I hope you guys know about these stuff. So I'll go to the next slide. So yeah, now the formal definition, like what do we do in regularization? We have the traditional loss function, right? We have the loss function, which is the sum of the squares of the difference between the actual output and the predicted output by the output which our model predicts, right? So we have that loss function. We add a penalty to it. We add a penalty term which is of the form of the lambda times summation of modulus of all the parameters raised to the power n. All right, lambda here is known as the regularization hyperparameter. All right, so what do I mean by parameter? All right, I'll just quickly explain what I mean by parameters. We have uh, you guys know about regression, right? Obviously, so we'll have y equal to wait, I don't have proper writing tools to write on the board properly, so excuse me for that. So yeah, we have beta naught plus beta 1 x1 plus beta 2 x2 and so on, right? All the coefficients which our model predicts later, like all the coefficients, like we perform certain tests and we predict these coefficients, right? These are known as the parameters. Like I mean, whenever I say parameters, I mean these terms, right? So yeah, so now that's done, right? So we uh, we take the modulus of all those stuff, and then we raise it to a power n, and then we sum it up, and then we multiply it with the factor lambda, which is hyperparameter. I'll get to the difference between parameter and the hyperparameter later. So yeah, we add this penalty term to the loss function. All right, so we have like various types of regularization based on this value of this n. All right, so like what happens when we add this parameter? Basically, like why do we add this parameter? When we add this parameter, what happens is that values of all the sorry, what happens if we add the penalty term? All right, sorry, excuse me for that. So if when we add the penalty term, the values of all the parameters, the absolute values of all the parameters decrease, all right, compared to the normal original loss function. Like when we have a model which is the traditional model, like without regularization, we have the loss function, the traditional loss function. We minimize it, we get the values of parameters, right? Now, if we add this penalty term and we minimize it, we get new parameters, right? The absolute value of this new parameters would be lesser than the absolute values of the older parameters. So how that happens, right? So we have the we have the loss function, right? We have the loss function. This is the traditional loss function, summation of y actual minus y predicted square plus the penalty term, right? Yeah, I'll just leave it. So we basically what we do is we try to reduce the loss function, right? So when we try to reduce the loss function, we obviously try to reduce both these terms. Now, when we take the gradients and back propagate and all, we try to reduce both these terms, right? So what happens when we reduce this? What happens when we reduce these terms? When we reduce this penalty, when this penalty term gets reduced, is that values of all the parameters get reduced, right? So basically, when we add the parameter, I mean, we add this penalty term to the loss function, what we're trying to do is that we're reducing all the absolute values of the parameters, right? So yeah. So what happens when the values of the parameters become less? When the values of the parameters become less, the coefficient of all the higher degree terms which our model is trying to predict, right? Our model basically tries to predict a function which appropriately fits the training data set, right? What happens is that that in that function we'll have higher degree terms, and when we reduce the parameters, when we reduce the absolute values of the parameters, the absolute value of the coefficients of those high degree terms would become less. And that in turn makes our model less complex. So what I'm trying to say is that if you have a function, if the values of the coefficients of the higher degree terms is less, suppose we have, suppose we have y equal to x plus x square and so on till x power 9, right, with coefficients, of course. If we reduce these coefficients, I'm trying to say that our function is simpler compared to the previous function, right? So I'll give a simple example on how that happens, right? So wait. So yeah, consider this graph, right? And then like, let's say these points are part of the training data set, and we're trying to find a polynomial basically which tries to fit these data points. This is these training data points obviously represent the sine curve. So we're trying to find a polynomial which approximates the sine curve. The model directly can't like give out the sine function, right? That's way too difficult for the model. So what we're trying to predict is that we're trying to predict a function which approximates the values of the values of all the new points which we add properly. So let's say if our model is underfitting. So basically what happens is that we get something like this. Maybe we have a straight line, maybe a bit more complex than that maybe, but yeah, you get the idea, right? We get a very simple model which doesn't generalize to every point, right? This is the case of underfitting. This is case of underfitting, right? So what happens in case of overfitting? How does it look like? How does the function look like? The function might look like something like this, right? We'll have the function like to generalizes to the training data set too much that like that a model becomes too complicated. So if at all we need what's the value of this, like we're trying to find the value of this point at the during the test time, we should get this value, all right? We should get this value, but instead what we get is that we get this. This is obviously not a better fit, right? So what would be a better model? What would be a better function? Wait, I'll change the color. A better function would be like somewhat like this, right? Like, yeah. So what like the observation that we're making is that this function would be of some would be of the order of x power 5 or something, and whereas this overfitting function would be of x power 9, x power 9, x power 10, x power 15, something like that, but higher. And this underfitting function would be like x or something, x or x squared or something like that. So what we're basically saying is that, what I'm basically trying to say is that when we as we keep on including higher degree terms to a model becomes complicated. So when we reduce the coefficients of all the higher degree terms, a model becomes simpler. A model doesn't overfit. So when we add the penalty term, we're basically trying to reduce the values of all the absolute values of all the parameters, which in turn reduces all the values of the coefficients of the higher degree terms, and which in turn makes a model less complex and simpler, right? So basically, this is the idea behind regularization, and I hope you guys get it. Like, if you have any doubts, this is all simple stuff till now. Like, if you have any doubt, you can unmute and ask, or put it up in the chat. Okay, no doubts. I guess I'll just proceed to the different types of regularization, right? So yeah. So basically, I forgot to mention these two. When n is equal to 1, it's known as L1 regularization, and it has a special name. It's lasso regression. It's also known as lasso regression. All right. And similarly, when n is 2, it's L2 regularization, which is also known as ridge regression. So basically, these two are the most common types of regularization that we use. All right. So I'll explain why we don't use L3, L4, L5, and all in a moment, right? So I'll try to explain all both these lasso and ridge regression in detail, but by using a two variable linear regression. All right. So what we basically do in a two variable linear regression is that we're given a set of points and we try to find the best fit line among them, right? So if suppose we have points like these, we have to find a line which like fits the data set properly, like the line for which the value of the traditional traditional loss function is lesser. So in this case, this the traditional linear regression works perfectly fine. All right, you get a proper line which is a good fit. So basically, I forgot to mention this, but why am I just using two variable linear regression? You can like apply regularization for like complex models. It's basically meant for complex models only, but I'm explaining it using a simple model because it's easier for you guys to visualize as you guys are taking it up the first time. So yeah, so yeah, I'll just proceed. So in this case, the traditional case of linear regression works like very well, so it works properly. But what about this case? We have only 2 points, right? So this is pretty trivial enough that the line which a model predicts should pass through these 2 points. That's basically the point of linear regression, right? We're trying to find a best fit line, and obviously this is the best fit line. So there is a problem in this data set, right? So basically all these this is the total data set. The green along with the red points is the total data set. And what we're doing is that we're having only these two red points as the training data points, and all these green points we use it for testing a model whether it's working properly or not. So but the line which we predict is obviously not a good fit, right? See, like these points are too far away from the red line, right? So what happens when we do regularization? We add the penalty term, right? So what happens when we add the penalty term is that we get the blue line. We get a line with a lesser slope, right? So we basically get the blue line, which is obviously a much better fit. I think this is intuitively understandable as well. So what I'm trying to say is that the takeaways from here are that when we do regularization, what happens is that the slope of the line which you're trying to predict becomes lesser, right? So basically what happens here is that the basic principle behind regularization is that when we have data with huge bias, it will have less variance, right? So so what we're trying to do is we introduce a bit of a bias, right? So in this case, the blue line has a bit more bias than the red line, all right? So and that results in the lessening of variance by a huge amount, right? So we have huge variance in this case, in the case of the red line and very less bias, and we introduce a bit of bias and we get the blue line, and now the variance is much lesser compared to the red line. So that's the basic principle behind regularization. All right. So yeah, so we can see that the blue line is a much better fit. All right. So yeah. So lasso regression. Now we saw about ridge regression. It's the n here is 2. So what happens in lasso? Lasso, the n here is 1. All right. So basically everything is the same. All right. Lasso is very similar to ridge. It differs only in one thing basically. So so I forgot to mention that in case of ridge regression, what happens is that we have this lambda, right? If we keep on increasing the lambda, what we are observing is that the slope of the line which a model predicts keep on becoming lesser, all right? And that makes sense intuitively as well, because when lambda is too high, what we're trying to say is that the parameter should become redundant, right? So basically what happens is that when we increase when the parameter becomes redundant, we'll have just a straight line. It won't depend on the x, right? Y equals some constant. That's what we'll get. So yeah. Whenever we increase lambda, we get a line with a lesser slope, which is less steeper. The line will be less steeper, right? So how does lasso differ from ridge, right? So in ridge regression, the slope tends to 0 only when lambda tends to infinity, right? Like this won't lambda, like in ridge regression, what happens is that if we keep on increasing lambda, slope will keep on decreasing, right? And the slope will become 0 only when lambda is infinite, all right? So basically the curves will asymptotically touch each other. All right. So, but that's not the case in case of lasso regression. In lasso regression, what happens is that if we increase lambda, if lambda crosses a particular threshold, the slope becomes 0. Like you don't need to wait till lambda goes to infinity. All right. So because of this, what happens is that if there are any useless parameters in the model, what happens is that in case of lasso regression, they go to 0 quickly, because we just increasing lambda, and then after lambda crosses a particular value, the parameter becomes like null and void. Like the parameter is basically not relevant to a model for after lambda crosses that particular value. So what happens is that when we have useless terms, when we increase lambda after that threshold, those useless terms useless parameters get nullified like quickly. But whereas in case of ridge regression, in order for the useless parameters to get nullified, we have to wait till lambda tends to infinity. That's too much, right? That we can't afford that. So in those cases, we use lasso. So but we have a disadvantage, obviously, in case of lasso. What happens is that if we have a useful parameter to the model, like I guess you guys get what I mean by useful and useless parameters. Like useful parameters is that the parameters which predict, like which have an influence on the data set, whereas useless parameters doesn't have any influence. Like you can even take the what can I say? You can even take the angular velocity at which the Earth's rotating right now to be a parameter for your model, but that's obviously not related to the model, right? So so if we have that as a parameter, we want a model to make it 0 as quickly as possible, and in those kind of cases, we use lasso regression. So so when do we use lasso and when do we use ridge, right? So we use lasso regression when we have a lot of useless parameters, And we use ridge regression when we have a lot of useful parameters. Like I'll explain what we do when we have both. Like for the intersection case, that's a specific model. I'll explain that as well. So note that even in case of ridge regression, even as lambda tends to infinity, the parameters don't become zero exactly. They just tend to zero. Even as lambda tends to infinity, you won't get zero exactly. The parameters will just tend to zero, right? So Lasso in that case is much useful compared to ridge when you have useless parameters. At the same time, when you have a lot of useful parameters, ridge comes into play. Ridge is the better model, right? Uh, and the model which Lasso induces is known as the sparse model, right? Because uh, most of the almost the all the useless parameters go to zero, and we have only sparse parameters, right? So we call it a sparse model. So yeah. Now I'll just go through a bit of maths to explain how and why the parameters become zero in case of ridge and zero in case of Lasso and not in case of ridge. All right. So yeah. First, let's see about what ridge, I guess. Yeah, we can see about ridge. Yeah, wait. Yeah, so I'll just try to plot the graph of the loss function versus the slope of the line which a model is predicting. We're still in that two variable linear regression, right? So slope, we can just analyze slope and lever, right? So and excuse me for taking the zero of the slope axis to be here instead of here, right? This would make the diagram look a lot cleaner than when I take the zero there, right? So this is, let's say this is 1 point, right? So uh, uh, can you guys guess like how the graph would look like in the chart or something? I'll just wait for like 5 seconds. Like just the loss function is the slope graph. What shape is it, like mathematical shape? Any few, like you can unmute as well, or you can like type it in the chat. Like, yeah, it's non-linear for sure. Like, be more specific, right? Like a bit more specific. Come on. It has just squares, right? Come on. Is anyone trying to speak? Like, I just heard something. I'll even write the function if you want. Right? Wait. So we have loss function is summation of what y actual minus m minus mx. Excuse my handwriting. Right? This is funny. This is y actual, right? I'll just read it out to make it clear to you guys. This is y actual. This is mx. M is the slope, right? M is the slope which we're trying to predict, and this is the intercept, right? And plus lambda times m square, mod m square. Doesn't make a difference adding a mod or not. So yeah, I'm asking you guys, what will the graph of L versus M look like? We have squares, we have linear terms, we have constant. So it's pretty obvious, I guess. It's not x cube, right? We have only m square. We have only m squares, right? So it should be a parabola, right? We have m square here. We have only m square here. We don't have any m cube or m power 4 terms, right? So it should be a parabola. Is that clear? Like to Kunal, you just type yes. Yeah, yeah, fine. Okay, I wasn't able to see that. Yeah, yeah, sure. So it must be a parabola, right? I'll just remove this stuff. So now this is a pain. how to draw the parabola. Right, this is one parabola, let's say. This is another parabola, let's say. This is another parabola. Okay, this looks surprisingly better than the trial versions that I did while preparing for this. Right, so these are the slopes which our model will predict, right? So let's say this parabola is for some lambda 3 and this parabola is for some lambda 2 and this parabola is for some lambda 1, right? So I just mentioned that as we increase lambda, the slope which our model predicts will become lesser, right? So can you guys just quickly type in the chat the order of lambda 1, lambda 2, lambda 3, like just compare them, right? Quickly, come on. This is simple, right? I just gave the hint right here. As the value of lambda increases, the slope which a model predicts is lesser. And the slope which our model predicts would be these stuff, right? This is pretty clear, I guess. A model predicts these slopes, right? Come on. Just write 1, 2, 3 or something in ascending order. Come on. It's not too much work for you guys. I'll just wait for 20 seconds and I'll continue. Yeah, sure. It's 1 greater, 2 greater, 3. Okay, Ganesh Kumar. It's actually lambda 1 greater, lambda 2 greater, lambda 3, right? The what I said is that as lambda increases, wait, as lambda increases, slope which our model predicts would decrease, right? So the slope which lambda 1 predicts is the least. So lambda 1 should be the largest, right? So lambda 1 should be greater, lambda 2 should be greater, lambda 3, right? This is just simple math. This is nothing, right? Come on. Like, is it clear? Like, if anyone has a doubt, you can like ask it in the chat, or you guys can unmute. Like, Raja Mundri Ganesh Kumar. Like, is it clear for you? Just type yes or no in chat. Yeah, sure. So I guess this is pretty clear now. Lambda 1 must be greater than lambda 2 must be greater than lambda 3, right? So what happens when lambda tends to infinity? How does the graph look like? Wait, this is the 0, right? Yeah, the graph would look somewhat like this, like just straight. The minimum would be 0. As I mentioned, as lambda tends to infinity, the slope will become 0. Slope which a model predicts will become 0. So the minima would tend to 0, right? Would tend to 0. Would not be exactly 0, but tend to 0, right? And these lines would not be exactly straight lines, but would tend to be straight lines, right? So yeah, this is actually parabol only yet, but yeah, sure. So I thought you guys would ask a question here, like why does all the parabolas touch at this point? Like, is that a doubt or? Okay, I'll just go on to explain it. All right, so uh, why does the value of the loss function at slope 0 is independent of all the lambda 1, lambda 2, lambda 3? Oh fuck, I have to write the loss function again. Okay, it doesn't depend on the okay, wait, I'll just write it. Y actual minus y predicted square plus lambda times summation of mod m square. Right, so when the slope is 0, m is 0, right? m is 0. So m is 0 means this term is 0. So it's in the loss function will be independent of lambda, right? I think this is pretty clear, right? This should be clear, right? Because we've done tons of LCD and calculus for JE, so this must be pretty clear, I guess. So yeah, when m is 0, the model here won't depend on lambda. The value of the loss function won't depend on lambda, right? So yeah. So as we increase lambda, what happens is that the parabola just becomes like this, and finally it will become like this. Finally, this is that point. Maybe finally it would be like this, right? So I hope this is pretty clear. Like if you have any doubt, you can like just unmute and ask, or you can even ask it in the chat, right? I guess. So yeah, this is fine, right? So now we'll look at ridge regression. No, this is ridge actually. We'll look at lasso. Now trying to predict the graph of lasso is not as easy as predicting ridge. Ridge was just a parabola, right? But we have modern stuff here in lasso, so it's a bit difficult. So I'll just directly go on to write it, just draw it directly, right? Uh, so what happens is that this is something. This is what this is the graph for one lambda. This is the graph for the second lambda maybe. This is the graph for the third lambda. This is lambda 1. This is lambda 2. This is lambda 3. So obviously again lambda 1 is greater than lambda 2, greater than lambda 3. So like what difference here between lasso and ridge is that we can see that in case of ridge, the slope tends to 0 only as lambda tends to infinity, right? That point which I mentioned earlier is pretty clear, I guess, from this graphs. So what happens in case of ridge? What happens is that first initially you'll have your graph will be something like this for initial lambdas, but after lambda crosses a certain value, you would have graphs like this, like this part of the graph would go missing after lambda crosses a particular value. Like this is because of the point of non-differentiability, right? We have a modem, so the graph is bound to have a point of non-differentiability at 0 exactly, because the mod changes value at 0, right? M equals 0, right? So we have a point of non-differentiability here, and as we increase lambda, this part disappears, and we'd have only this, and this becomes the minima. Like after lambda crosses a certain value, so slope 0 becomes the minima, right? So what that implies is that after lambda crosses a certain value, the slope which a model predicts becomes 0. So what that implies is that the parameter becomes null and void. So we can basically conclude that uh, lasso makes the parameter 0 much quicker than ridge, right? So yeah, that's basically it regarding lasso and ridge. Okay, so I'll continue using the slides now. So yeah, there are some important points regarding the lambda, right? Lambda is also known as the regularization hyperparameter, all right? So one thing is that you guys have to know the difference between a hyperparameter and the parameter. I just explained what a parameter is, right? Parameter are the values which you find using the model. Like after running the model only, you'll get to know what the values of those terms are. So parameters are those things. Whereas what a hyperparameter is that you define it in the program only. Like for example, learning rate is a hyperparameter and stuff. Like so, yeah, I guess you guys get it. Like you guys know what learning rate is, right? After finding the gradient, you have to multiply it by a factor and subtract it from the actual value. That factor is known as the learning rate, and it's user dependent only, right? We only will define what that thing, what learning parameter is. So learning rate is, sorry. So those kind of quantities are known as hyperparameters. So and lambda is a hyperparameter because we are only defining what lambda is, right? So yeah. So first point is that lambda should be non-negative, and that's pretty trivial, I guess. So if lambda is negative, it kind of defeats the whole purpose of regularization, dude. So you'll have what? You have loss equal to the traditional loss function plus lambda times summation of some shit, right? So what happens is that as we try to reduce lambda, we try to reduce this term as well, and therefore the mod term decreases. So, but this is the case when lambda is positive. So what happens when lambda is negative? Like, let lambda be negative and we just replace lambda not equal to minus lambda. Okay. This is the same thing as adding lambda, right? So what happens? Lambda naught is positive now because lambda is negative. So when we try to minimize the loss function, we'll actually try to increase the value of this when lambda is negative. So we try to actually increase the value of parameters, and that kind of defeats the whole purpose of the regularization, right? So because of that, lambda should always be positive. Non-negative actually can be zero as well. Zero is the standard case, right? So yeah, as I mentioned, as lambda increases, slope of the line which a model predicts decreases, right? So that's pretty basic actually. You can just like easily derive it, I guess. So and then as lambda tends to infinity, the slope of line tends to zero in case of ridge, right? Not in case of lasso, right? Okay, I guess that is fine. And one more important point which I wantedly missed at the beginning is that I thought you guys would ask why we're not adding this, but in the penalty term we don't add the intercept. Like while explaining ridge regression, I've added only the yeah, I've added only the slope, right? I've not added the lambda times of mod c square. Like, why is that? Like, basically, y equal to c plus mx. We are trying to predict c and mx. So c is a parameter as well, m is a parameter as well. M is a parameter and c is a parameter as well. But we are not including c here. Why is that? Because we don't want our model to like depend on the choice of origin of a coordinates, right? So wait. So if we have something like this, right? We have something like this, and a model predicts a good function. Fine, we are happy. Now, if we increase the value of all the data in the training data set by a certain amount, like constant, right? All these values are the same. We want a model to just shift up, right? We don't want a model to change in itself. We just want a model to shift up. So that's why I'm not adding the C in the penalty term, and lambda is chosen by 10 cross validation as fine, I guess. So and then now elastic net. Elastic net is nothing. It's just a combination of L1 and L2. We just multiply the L2 penalty term with some constant and multiply the L1 penalty term with some constant. Just add it and then you're done. Like when is elastic net used? Elastic net is used when elastic net is used when we have a lot of useless parameters as well as a lot of useful parameters. So yeah, that's elastic net. So what else we have? This is another graph trying to explain why Lasso tends to zero quickly compared to the other two. So we have like I'm speaking about regularization like for 40 minutes now, I guess. So what's an application? Like, is there any application other than just reduction of the overfitting? Like, what happens? Is there any other application? So yeah, it does have a very good application actually. So in case of linear regression, the we have the number of parameters, right? So in order to predict a function properly, we need at least we need the number of data points in the training data set should be at least the number of parameters in the function, right? So yeah, as I mentioned here, the number of data points in the training set should be greater than or equal to the number of parameters, right? Otherwise, it's like you're having only one, you're having only 2 points, and you're trying to predict a plane through it. If you have only 2 points, you can find a line through it, but you can't find a plane through it. Like there are infinite planes, right? So we can't find a unique plane. So regularization comes and helps here in this kind of situations. Like in simple cases, it sounds kind of trivial, but you have a large number of if you have a the number of parameters is huge, and it's practically impossible to get a data set with that many data points in the training set, right? So basically, this issue can be solved by via regularization. Like if you have regularization, you don't need that many data points, right? So yeah, that's one thing. I'll just quickly explain the implementation as well. So here I'm just here we're just importing libraries and stuff, and yeah, we're just taking a random housing data set and then putting it in a data frame and stuff, right? So you have linear regression. I'm just like, I guess you guys know about all these stuff because I think linear regression was already, the implementation of linear regression was already explained in one of the previous sessions, right? So uh, I just like to show you guys that what we did is actually correct, right? So here the training error for the general traditional linear regression is 0.48, and the test error, the error in the test data set is 8.84. Just remember these two values, right? So now this is just like these are all input functions, right? This alpha is just the parameter, it's just the regularization hyperparameter, and then just choosing some alpha and then finding the this predicting model, right? So what we can see is that the error in the training data set increases. That's obviously true, right? Wait, I'll just show. Yeah, see, when we regularize, the error in the training data set increases, right? Previously the error is absolute zero. Now you have some error. So basically, the error in the training data set increases, and that's true. That's reflected here as well. It's 0.51 compared to 0.48, and the error in the test data set decreases. And what's important is the error in the test data set only. So this is pretty good, right? You have some difference, like not that big a visible difference, but yeah, sure, we have some difference, right? So same here as well, Lasso, and then I'm just trying to plot different curves. I guess you guys can read about this on your own. Like just look at it, you guys will be able to understand, I guess, if you just look at it. So as I have some more things to explain, I'll just brush through this. So we have bridge regression as well. Same thing. We have the error in the training data set has increased, and the error in the test data set has decreased, like by 0.2 only. But yeah, it has decreased. So here we are trying to actually find a suitable lambda by trial and error. So yeah, and then again here same thing, same stuff happens. The error in the training data set increases, and the error in the test data set decreases by a small amount, right? And then we have the implementation of elastic net regression as well. So I guess this and all is fine. The implementation and all, I think all are inbuilt functions only. So that's pretty basic, right? So what else do we have now? What we have, the most important method which we're going to discuss right now. Like this is more important compared to L1 and L2 as well. So yeah, dropout. So what happens in dropout is that previously L1 and L2 we were discussing for regression cases, right? So what shall we do in case of neural nets, when neural nets are involved? Right, when we have deep neural networks, they try to like they identify complex features and tend to like severely overfit the data set, right? So in order to minimize that, we use dropout. What we essentially do in dropout is that we randomly disable neurons and their connections. Like we have a neural network, suppose this is a neural network, we just like remove some neurons with some probability, like probability of this neuron being present in the model is some p, like there's a chance that even this could get dropped and this could have been present, something like that. I guess you guys get it, right? We just drop random nodes and their connections as well, right? The connections which emerge into the neuron and which emerge out from the neuron as well. So yeah, we just randomly remove these stuff. So remove these neurons. So how does that work, right? So effectively, what we're doing is that we're kind of training multiple networks. Like we do this for each. We divide the training data set into some. We do this actually for each training data point, right? So for one training data point, this would be the case. For some other training data point, this would be present, this would be absent, something like that. So what we basically doing is that we're training multiple networks, and then we're averaging all the results of all these stuff, all the networks, I guess. So usually, like if we have like huge amount of computation, like if we don't care about how much computation we do and all, the best machine learning model would be to like train a lot of models and then averaging the results. So like this kind of learning is called ensemble learning. Like I think it was taught in session 5. I think it was taught in session 4 or 5. I don't know. I don't remember. But yeah, I guess you can look this up. Ensemble learning, right? So yeah, but this would take a huge amount of computational time and computational power in case of like deep neural networks and all, where we have hundreds of layers and hundreds of neurons in each layer. So yeah, so while using Dropout, we ensure two things, right? So we ensure that the model is accurate and doesn't overfit, and then we also ensure that the computational time is much lesser compared to before. And why is that? Because in case of Dropout, while backpropagating, the number of gradients you're calculating is less, right? Because we're having lesser number of neurons in each step. So the number of gradients that you're calculating is actually lesser compared to the previous one, and so computational time would be lesser. And yeah, so if suppose the probability of removing this node is p, what we should do at test time, every data set, every neuron would be present. Only at the training time, for each training data point, you remove like random neurons and then train it and then average it. And then during test time, every neuron would be present, and then what happens is that in order to like compensate the leaving of this neuron in some of the training data points, we should multiply the weights which we get by this probability in order to ensure that balance, right? So yeah, so this is kind of basically, I'll give you an example, right, to get an intuition on how this should work properly. So basically, if you're trying to execute a conspiracy, maybe like, and you need 50 things to do, 50 things to do to execute the conspiracy properly without anyone knowing it. Uh, let's say we have two cases, case one, case two. Case one, we have only a single person who should do all the 50 things by himself, okay, and not get caught, right? And then case two, we have like 10 people. Each person should do five. Each person should do 5 tasks, and then execute the conspiracy. Which case do you think is better? Like it should obviously be case two, right? Because the possibility of error happening in case one is a bit higher than that in case two, right? So yeah, so basically dropout kind of works similar to it. Like we're just removing random neurons and we're just trying to cover up the mistakes that are learned as well. The models learn some wrong things as well while we are training. Like the model doesn't exactly learn all the correct stuff, right? So model learns some wrong stuff as well while training. So in order to not in order to reduce the effect of those wrong steps, we just take like multiple networks and just average it, like just superimpose it, I guess. So yeah, basically, this research paper, which was published on this dropout, is like pretty easier to understand, right? You guys can like usually, in my opinion, you guys should definitely look this up. Like I've provided the link here, right? So and apparently the author of this research paper is has a second name Srivastava, and coincidentally, uh, the person who's gonna teach next, Ashish, also has his surname Srivastava. Coincidence? I think not. Right. So with that, I'll just end. Right. So Ashish, I think you can continue. Ashish, are you here?
So yeah, am I audible? Can you take this control?
Yeah, you're on. I'll stop sharing now.
Oh yeah, thanks a lot.
Yeah,
Yeah.
Ashish,
Thank
I
you,
don't want
guys.
to. I don't want to stop on a very good joke, but maybe we'll take a short break till 3 and then you can start at 3 p.m. Is that fine?
Yeah.
Yeah, that's fine. Yeah, that's fine.
Yeah, that'll be great then. Maybe you can also share the notebook that you'll use on the groups.
Yeah. I'll share. I totally forgot to share. Sorry.
Yeah, guys, we'll start at 3 p.m. Maybe you can go take a short break and come back.
Archish, can we start now?
Yeah, you can start now.
Yeah, okay. So okay, so my screen is visible, right?
Yeah, man.
Okay, cool guys. So hey guys, so after the regularization, we'll be starting off with OpenCV. Now, this is a little bit of a deviation from the route that was planned out, but since computer vision is one of the key areas where deep learning is currently employed massively, and it has a lot of huge applications. So, and one of the main libraries that is used for uh, doing computer vision algorithms and processing is OpenCV in Python. So, up ahead, we'll be covering OpenCV, pretty basics of OpenCV, which will really give a good base for you in case you want to do something further in it. And but before that, a little bit of a theoretical knowledge about images, transformation, and convolutions. I'll just explain these to you in basics. If you have any doubt, we'll be later shifting to a Jupyter notebook where I'll be implementing all of these for you. So if you have any doubts, you can type it in the chat. I will answer it when I'm covering the notebook, or you guys can unmute and as well ask. So let's start off with what OpenCV is. So OpenCV, as you all know, is a very famous library for program that is used in programming and real-time computer vision in Python, C++, and C. So now, what is basically OpenCV used for? So OpenCV is used in areas where we use artificial intelligence or machine learning or deep learning algorithms, where there's a use of image processing. So before that, let's move on to a very fundamental topic as to how computers read images and how they represent images. Now, uh, computers as such can only read things in the form of numbers, and what we see images are basically objects and colors. So now this is difficult for a computer to understand. So computer sees an image as a matrix, and these matrix have values, numerical values, which are used to associate color spaces, which we'll be covering later. So now each cell of a matrix is what we call a picture element, or in short, as you know, is a pixel. So you guys can like see this example over here of A, which is like pixelated, and you can see the matrix representation that it has. It is filled with numbers. Now, so so this is what we call a pixel, and this is how a computer reads an image. So next up is how do we tell the dimensions of this matrix which is representing this image. So now you all must be very familiar with, like, when you download images from the net, you guys see a number, right? Like 1980 into 1080p, or 1200 into 720p. So basically those are the image height and width. So as you can see, dimension of a matrix is the image height times the image width. And there's one more thing which you guys don't see on the internet, but it is a very important part of this dimensioning, is this number of channels, which I'll explain to you guys as we are covering color spaces, because it just makes more sense over there. So now these pixels store values, and each value represents a particular color. So up ahead, yeah, so let's see what color spaces are. So to show these images in a colored format, or in a way that make in how we see it, we use the computers use something. They use something called as a color space. I think someone's unmuted. Like, if you can just mute yourself. So now color spaces are basically mathematical models, like functions that describe how colors are represented for a computer. And so they basically map a certain color to a certain number, and those numbers are usually 8-bit in size. So there are like various types of color spaces. We'll be covering 3 of them over here, and we'll be using those 3 in the Jupyter notebook as well. So the first color space that we'll be using is the grayscale color space. Now, grayscale color space is basically a one channel color space, meaning the image only has one layer, and that layer represent, and the values stored in that layer represent the color. So like you can see, this is a very blurred and pixelated image of possibly Abraham Lincoln, and these are the values of that these are the matrix values of this particular image. So as you can see, this image has only one layer and is completely represented in shades of black and white. So this is what we call a grayscale image. So a value of 0, as you can see in some places over here and here, is used to represent the darkest shade of black, or we simply call it black. And a value of 255, which is pretty hard to spot over here, but there's one over here. So this is used to represent white, and anything in between is basically shades of gray or white or black. And this is how grayscale images are represented. And coming back to dimension, so here the dimension will be the image height times the image width times 1, because we have only one channel. So next up, we have one of the most common color spaces that we are familiar with is the BGR or RGB color space, which stands for the 3 primary colors, that is the blue, green, and red. Now, not to be confused with BGR and RGB color spaces have the same basic fundamentals, but just differ in representation. So we'll see this in the Jupyter notebook, and it will be very clear to you guys over there. So here in this color space, each image has basically each pixel of the image has basically 3 channels. Like you can see over here, there's 3 channels, that is the 3 different layers to this image. And just like the grayscale image, each layer over here, instead of representing black and whites, represents shades of red, blue, green, and red in that particular order. It will be blue followed by green followed by red in a BGR color space. Now in an RGB color space, it will be a reverse of it. So you can just flip these layers, and that will give you the RGB color space. So here also it's pretty common. It's pretty simple. The pixel values are between 0 to 255. And for better understanding of this color space, you can think of this as a cubical model. So where you have you can see this representation of a cube here. So any shade that you want to represent will be a combination of those 3 colors, and you can spot it on this cube, and the combination of red, blue, and green will give you that particular color. So next up, moving to the next color space that we'll be exploring is the HSV color space, or the hue, saturation, and value color space. Now, this color space is not a very common color space in representing images as such. But this is a very useful color space when it comes to object detections and image classifications. So here, this color space also has 3 dimensions, 3 channels to it, and those 3 channels are hue, value, saturation value, and the third one is called value as such. Now, what you can imagine this color space as a cylindrical model. So what hue value represents is, if you were to take this top circular face of this cylinder, hue basically represents where on this color circle you will find yourself. So if you were to draw a 0 line over here, so a 0 line would correspond to shades of red, and moving all the way up to 120 degrees, like approximately over here, would correspond to you would find yourself with red, orange, yellow, and stuff, and then at 120 degrees is where the green begins, and that goes on for another 120 degrees, and then you find yourself with the blue color space. So the hue takes in values from 0 to 360. Next up, you have saturation. And saturation basically specifies the amount of color that you're using. So saturation is something like this. It goes from the inside of the cylinder to the outside all the way up to here. And if you were exactly at the zero value, you'd basically be seeing yourself in a grayscale color space. But as you move over here, it shows how much of the color you're using. And a shade of 100 basically at the edge of the cylinder represents the purest shade that you can find. And next up, value, it basically controls the brightness of the color, and it somewhat moves from the bottom to the top all the way up to the height of the cylinder. So the bottom represents a total black, that is zero amount of brightness. And as you move to the top, you find yourself with increasing brightness. So these are the three color spaces. Now up ahead, we'll be seeing what is convolution filters, which are the most fundamental and basics of image processing. And these are the basic stepping stones which are used in image processing. I mean, like, there's not a single image processing task that is without these convolution filters. And so to understand how these filters work, I'll be explaining you with 1D and 2D convolution. And since it is a very basic session, we'll stick to 2D convolution filters. And if you guys are interested, you guys can maybe follow it up. So convolution filters were basically an idea in signal processing, where what would happen is you would have an incoming signal coming in, and basically it would have a lot of frequencies, noise, and so you want to reduce the noise and get a proper range of frequencies. So what they would do is use a filter and pass the signal through this filter to get the desired output. So this is where convolution took its root. And 1D convolution, the basic which was used in signal processing, is the 1D convolution. I'll be explaining this to you, so because this is really important to understand how 2D convolutions work. So say you have this signal that is over here, which has the matrix values 1, 1, 0, 0, and so on. And so let's call this as matrix F, or you can call it as a signal F also. And you have the filter, which we usually call it as kernel. And so this kernel that you have, kernel G with the values 1, 0, and 1. So how convolution works is, first you take your filter and you flip it, basically invert it in the sense. So since this is a 101, if you were to invert it, it would still be a 101. But if you were to say have something like 2, 3, 5, and then if you were to invert it, it would become 5, 3, 2. And what we do is we take this kernel and place this one over here at the start of this one to begin the filtering. So what we do is take this one and multiply it with this one, take this one and multiply it with this 0, and take this 0 and multiply it with this one, and add all those values, and that is the value of this first output cell that you have one. Then next up, what we do is we take horizontal steps, which we call it as strides. Now, the interesting thing to note over here is you can have an stride of n steps as well. It need not necessarily be one. But in this example, we have taken a stride step of 1. So then we move to the adjacent cell 1 over here, and you can see that this process is repeated. And this process goes on until the end of the signal, and you get a final uh, final signal or output or matrix, whatever you want to call it. And obviously, this is a matrix with shorter dimensions than the original matrix. So this is the basics of 1D convolution. So next up, we move to 2D convolution, which is where we start diving into basics of image processing. So I've shared the slide with you guys. You guys can, if you want to read up, you guys can read up these steps that I've given. It's I'll be explaining it to you with the help of these images over here. Now 2D convolution is the same thing. Instead of the signal, we have our image matrix, the source matrix, and we have a kernel matrix, which is going to be the filter, and we have the output matrix, which will be generated by applying this filter on this image matrix. But in 2D convolution, it works a little bit differently. Say you want to apply the filter to this pixel element 99, that is the uh, uh, element 2, 2. So what we do over here is, instead of applying the 0, that is the start of this filter matrix, we center the filter matrix on the pixel on which we want to apply the convolution. So here we want to apply it on 99. So we center the center of this matrix, that is 5, over here, and the same steps follow. So first you would be flipping this matrix both horizontally and vertically. You guys can try flipping this, it will give you the same matrix basically back, but that is like an essential step. First you flip it both horizontally and vertically, then center it on 99, and you repeat the same step, multiply each cell of this with the corresponding cell of this, and add those values as you can see over here, and that gives you the result that you want in this particular cell of the output. Now, and then again you follow it up with a stride of n steps and repeat it till you have covered the whole of the image. But an interesting thing is, say you were to like convolute this element 105. So if you were to center 5 over here, you would find that the elements of this kernel matrix on the top row and on the left row will have no cells over here. So here is what we do to avoid this is, we do a zero padding. This basically we add rows and columns of zeros, which basically makes no change to the image that we are representing. Uh, but we do this so that the convolution is evened out, and then we repeat the same step. We do a cell by cell multiplication and add those cells, and you basically get the final output over here. So this is basics of 2D convolution. And next up is something which is another step in, which is another very important step in image processing. And this step is usually either used in pre-processing or post-processing of the image. That is to either filter out this image before you process it, or beautify the image after you have done processing it. And that is called as morphological transformations. And so these are basically set of operations. Now, as you saw, convolution filters were basically set of operations that are working on the pixel values as such, and not on anything else. But these these morphological transformations work on the shapes of these images. So we have, I'll explain to you two basic transformations which when combined together have a lot of various applications which we'll be exploring. So the basics, first basic one is erosion. So I'll explain to you what erosion and dilation is. You guys can read how they work. It's pretty self-explanatory. Even if you see the images, you'll get a feel of how they're working. So basically, what erosion does is, basically you have a object of interest in your image, and say what you want to do is, it's either too noisy or too blurry, and you want to like reduce that image size so that it becomes more clearer for you. So what we do is, we use erosion. It basically erodes the boundaries of the object of consideration. Like you can see in this image over here, this J that was like pretty blurry over here, and the edges were not sharp. You've eroded it. I mean, it does no help over here, but in like certain applications, when you see the applications, you'll understand that it is actually a lot useful. And next is dilation. Dilation is when you have an object of interest, and you want to basically increase the object area because it is too thin or too small for you to detect properly. So we use dilation. As you can see, this image over here, it has been dilated, and you can see the object size increases. Now, working with this image is much easier than this image if you're comparing them on a relative scale. So this is the basic theory that you needed for before we move on to the Jupyter notebook. So I've shared with you guys the notebook, and I would highly recommend it if you guys can like follow this notebook, because this it would be a lot helpful for you, and you'll probably understand it much better. So before we move any further, we'll be cloning this Git repo that I've created for this for the summer school. So you guys should probably run this cell before you do anything else in this notebook. So this Git repo has two folders. Basically, one is images and one is tasks. So first we'll be seeing all these basic functions with the help of images, and then I've planned two simple tasks for you guys, which I'll be walking you through, and you guys can execute it on your end. I'll just show you the output from my side, and next up, you guys would want to move into the summer school repo. If in case you want to see what all is there, you can just click on the refresh, and this repo comes up over here, and you guys can view the files and contents. So first up will be a very the most basic functions, that is reading, displaying, and writing images. So the functions that we'll be using over here are cv2.imread, cv2.imwrite, and cv2.imshow. So cv2.imread, as the function tells, is basically to read the image from a particular path. And this has two parameters. One is the file path from where you want to read the image, and next is the flag. So flag usually takes in two values, a flag value of 0 or a flag value of 1. And a flag value of 0 takes the image in the grayscale format, and a flag value of 1 takes the image as a BGR format, a BGR color space. And next up is the cv2.imwrite. This is used to write images to a file path, basically save, like if you worked on an image and processed it and you want to save this image in a folder, so we use this function. And so here it has two parameters. One is the file path where you want to store the image, and one is the variable name, that is the variable which was holding that processed image you finally got. And the cv2.imshow is used to display images. So now one problem with collab notebooks is cv2.imshow somehow crashes the notebook. So we'll be using a patch these guys have made, that is the cv2_imshow. But if you are going to be using on a regular Jupyter or Python IDE or any Python IDE, you might want to use this one. This still works over there. And one more function which I have added is, which won't be of use in this notebook, but it's certainly very helpful in Python IDEs, is cv2.waitKey. Now what happens in IDEs is, when you display an image, it basically opens up another window, and that window closes in a matter of milliseconds. So you won't be able to see the image even though your program has been executed. So there we add a wait key with a delay parameter that waits before closing the window. Now this delay parameter is in milliseconds, so be sure of that. Or in case you want to display the image for an indefinite time before you press any key, we use the set the delay parameter to 0. So that will help you guys. And so yeah, here we'll be just importing a few useful packages in the collab patch, and above here grayscale and one in the BGR color space, and I'll be showing you guys the matrix values of those images, and then we'll be displaying one of them using the imshow function. And for easier understanding, I've chosen to display images using matplotlib because it helps you plot images next to each other and gives you a better feel for it. And so you guys can like see that as well. You guys can still use the imshow methods. I've just commented out those if you guys are interested. Okay, so now as you can see over here, the first image that we inputted was in the BGR color space. So you guys can see this image has, you guys can see this this channel over here. This was and this channel is the green channel, and this channel is the red channel. So you guys can like clearly see there's 3 channels for each of this. And next image we had was in the grayscale, and you guys can see this is the grayscale image with just a single channel, having the dimensions of the height and width of the image. Now one thing to note is, when you're plotting using matplotlib, the basic color space in which matplotlib works is RGB color space instead of a BGR color space. So I have converted this BGR image to RGB image. This is just next up how to convert color spaces. But in case you are working with matplotlib, make sure to like change the color spaces so that you guys can see it properly. Like this is how imshow will show you the image. It's basically without any borders and stuff, and it will show you the size as it is. But if you were to use a matplotlib method, and this it will show you with all these borders and filters, so and titles as well. So this image is the one which was in the BGR color space, and as you can see, it's pretty bluish and stuff. So yeah, it displays the image properly when it's in the RGB color space, and this is the gray. So next up, yes, we'll be seeing how to convert between the color spaces. So this makes use of the function cvt color. Make sure of the name over here. There's a capital C. So this again takes in two parameters, and those two parameters are the input image and the flag. So input image is again variable name of which you want to convert the color space of, and flag basically specifies the type of conversion. Now, listed down four basic conversions that we'll be using throughout this Python notebook, which you guys can refer to. I mean, it's pretty self-explanatory. I'll just explain one of these to you, like gray to BGR signifies it's changing from the grayscale to the BGR color space, and all the others follow the same pattern, and you guys will get a feel of it if you just read it once. So here again, we are going to be reading three images, one in grayscale and two in BGR, and we are converting one of them. We'll be converting each of them to BGR, grayscale, and HSP color space. So you guys can like execute this, and you guys can like see this BGR image has been changed to grayscale image, and this uh, uh, BGR image has been changed to an HSV image. And so yeah, you guys can like go ahead and see, and I've added some more images. You guys can feel free to use those images and change the well. And next up, what we'll be using is we'll be seeing how do we use 2D convolutions in Opencv. So before that, like there are two functions that you guys should know before using this. Is one is an numpy function, that is dot array. So this is used to create an matrix of a particular data type which you want in a numpy as a numpy array, because numpy is much better at handling multi-dimensional arrays than normal Python functions. So we use this. Uh, so here the two parameters that we'll be taking in are the matrix. So matrix is basically the matrix or the filter which you want to create. You guys can like give in random values. I've mentioned a few filters below, which I'll be explaining to you guys as well. And next is the data type, is basically the numpy data type which you want the array to be. I've given you three examples over here. We'll, however, be using this np.int or np.float32. And next is the main Opencv function, that is cv2.filter2d, and this has three parameters. One is the source matrix, that is the image on which we want to apply the filter. One is the depth out matrix, that is basically depth of the output matrix. Now this makes sense when this is basically denoting the number of channels the matrix you want the output matrix to have. Now this makes sense when you are using 2D convolution on an image that is basically has three dimensions, that is
Hey Ashish, I think your screen stopped sharing. You there on me?
Sorry guys, there's a cup from my end. So is my screen visible? Like can someone confirm?
Yeah.
Thanks a lot. Yeah, sorry. So we were exploring the CV2, the filter 2D function. So the depth of the matrix is basically used when you are applying a 2D convolution on a three-dimensional matrix, that is a matrix in VGR or Rgb color space, or say an HSV color space. So the depth of the matrix, for now you don't have to worry about it. You can just use -1. -1 basically means the matrix is going to be of the same depth as your input image, and kernel is basically the filter matrix that is going to be used. So now before we move and see the working of this function, I'll give you some filters over here that have some particular functions. Now, one of them is edge detection, as and the name is pretty self-explanatory. Edge detections is when you want to detect edges in your image, which will be further used in image processing. Like one example is in autonomous driving, uh, autonomous vehicles. Edge detection is used to like detect cars or objects on the road, like so to identify where a car is and where the car's edges are, to make sure it can find an optimal path. So I've given you like three filters over here. You guys can like try these out. Next is image sharpening. So image sharpening again has uses in uh, image processing, where you have an image and it's say has a lot of noise and it's blurry, and you want to basically like see some features from it. So you basically use image sharpening to highlight those features. Now one good example of uses of image sharpening is in the images that you get from telescopes or space centers and the rover inputs. So there, basically, the image usually is a low resolution image because of the complexity of the image that is there. And once you receive it, to basically like to see more and identify more features in it, we basically use an image sharpening function. And next is blurring. I have mentioned one particular function, one particular filter that is called the box blur. Now, the basics of blurring is you basically try to smooth out the image and make it a low filter, or what we call it as a low frequency image, and to to use it in certain tasks in image processing. So up here, we'll be again taking in two images, one in the VGR color space and one in grayscale, and applying two filters which I've created using the numpy.array function. So I'll be printing the filters and then showing you the output images. So you guys can see this is the filter that we used, and these two are the filters. And as you can see, the first one was basically an edge detection filter. So we applied this on the first image, and you can see it's done a pretty good job of finding the edges on the main player that is here, and very faint edges on the player that is there standing in the background. And next up is this image where we use the image sharpening function on this grayscale image. Now you it might be difficult for you to like see the contrast because this has been like sharpened to a decent extent. You guys can like see it. In case if you want to see it on bigger scale, you guys are free to use the CV2 underscore I am show function. It will you can probably see it much clearly than you can over here. And so next up is we'll be seeing how to use the basic morphological transformations. That is the erosion and dilation. So erosion has the function cv2.erode, source, kernel, and iterations as its parameters. Now the source is basically the input image, and kernel is basically the kernel that you're going to use for erosion, and iterations is how many times you want to erode the image. And so here, one thing to be noted is your input image should always be in grayscale because it works only on grayscale images. And so you must always take care of that. And next is use dilation. So the function is dilate, and it again has the same parameters, pretty much the same explanation as the above. And so here we'll be uh, reading an image and applying these uh, transformations. And so here I've chosen the J image that was there in the presentation. You guys can like see the eroded and dilated images. Now, as I told you, erosion and dilation when used in sequence have very useful applications, and they tend to like create a sort of transformation which we typically refer them to as advanced morphological or other morphological transformations. So I'll be explaining to you 5 of those here. One is the opening. So opening is basically just erosion followed by dilation. So what it does is basically removes these noises that are there over here. Now, one application of this is in fingerprint processing. When you give your fingerprint, so our interest is basically the edges and contours of uh, of your finger, and when you give them, there's certain amount of noise like this on the outside. So you want to remove these noises, so we use opening over there. And next is closing. Closing is basically the reverse of opening. Is basically when we use opening, when we use dilation followed by erosion. So this basically does the job of like covering small holes. Say you have like a image, and it is like a pretty noisy image which leaves out these noises in the middle, like these dots you can see. So we use that to close this to close them. And next is morphological gradient. So morphological gradient is just the difference between the dilated and eroded image. So you can see over here this. And next, these two particular last two transformations are basically really important and have a wide array of applications in image processing. One is the top hat and the other is the black hat. So top hat is basically the difference between the input image and the opening of the image. So now the output that you get is varied on what type of kernel you use. So here we use the 9x9 kernel, and to do the opening of the image, and then the difference was taken. So this is what the output looked like. And black hat is the difference between the closing of the input image and the input image. So this is what the output looked like when a 9x9 matrix was used. And the function that was function that we use is cv2.morphology ex, and this has 3 parameters. One is the image, that is the input image in binary input image which we want to use the transformations on, and this again it has to be in binary. Next is the operation or the transform parameter, and this is basically what type of transformation you want to carry out. So here I have given you the 5 parameters that you can use to do the following the corresponding transformations, and next is the kernel that you want to use for transformation. So below we'll just look at what the application of top hat and black hat is. Now top hat filter, what it does is, if you have a very dark background and you want to like say enhance very bright objects from it, but these bright objects are very minute and you cannot like normally you use any filter operations on them to see them. So then we use the top hat filter. So I have done the top hat filtering for this one particular image, and I'll show it to you guys. So you guys can see now here the first thing to do is you have to identify a dark background. So if you see this particular section over here, this is like a very dark, the background is relatively darker compared to these white things that are flying around. And so you can see it does a pretty good job of recognizing those white things all over this dark backgrounds, like say over here and here and here. So this is what top hat is used for. And black hat basically does the reverse of it. Say you have a very white background and you want to identify certain dark features on it which are very minute. So then we use the black hat, and you guys can see over here. As you can see, the players' shirts are like basically white backgrounds. Like they are like white backgrounds, and you can see the Emirates that is written and the stripes. they're basically minute dark objects on these white backgrounds. So this black hat does a pretty good job of identifying those stripes and emirates that is written around. So this is like, I won't explain to you how this code is working. You guys can see. It's just for like an application purpose of sorts. You guys can like feel free to write your own code to implement these other morphological transformation on images that are there in the sample image folder. And so next up is a pretty interesting part. We'll be seeing how do we detect edges in using Opencv. So before detecting edges, we'll be looking at the Sobel operator. Now, one fundamental step in detecting edges is because once there is an edge, there's a like a very high change in the pixel values of the neighboring areas. So what we do is we basically make use of gradients to detect these changes in pixel values. And so to do these gradient operations, we use something called a Sobel operator, which is basically does calculates the approximate uh, first order derivative of the pixel intensity curve. So here we use we run two derivatives, one in the x-axis direction, we call it as the gx, as you guys can see over here, and one we run it in the y-axis direction, in the vertical direction, and we call it as gy. And so a Sobel of kernel size of 3 that we use in gx looks something like this, and a Sobel operator in gy in of size 3 looks something like this. So we basically use these transformations on the image, and we calculate an approximate gradient. Like if you had to combine those two you basically combine these two gradients in the final edge detection process. We combine these two images to give the final output. uh, and so there the approximate gradient is calculated by two methods. One is the square root of gx square plus gy square, or the other one is the mod gx plus mod gy, and both of these tend to give you the same or approximately close results. So you don't have to worry about that. So the function that we use to basically run a Sobel operator on the image is the dot Sobel function. Now this has parameters as source, d depth, x order, y order, and k size. So source is basically the image on which you want to apply this Sobel operator. The d depth is the depth of the output image. Now I have given certain depths that are supported, but in this notebook we'll basically be using the CV underscore 64F d depth parameter. X order is the order of the derivative in x direction. Y order is the order of derivative in y direction. And k size is the size of the Sobel kernel that we are going to be using, and it always is an odd kernel of the size either 1, 3, 5, or 7. So here we'll be running this code. So we have made use of the reading writing functions, and before we run a Sobel operator, we basically apply a Gaussian blur to the image to basically make it a low frequency image so that it's much more easier to detect the edges. So here I've used the Gaussian blur function. Now this will come up in the next section, and I'll be explaining it to you over there what a Gaussian blur function does and how it works. But for now, you can just like take it for implementation. And so we run a Sobel operator first on an BGR image and on a grayscale image. But let's start with the grayscale image. Now you can see this. I've run Sobel X on this, and if you see the structure of the Sobel X kernel, you can see it has image. It has pixel values in the vertical direction, and so this basically is used to help in detecting vertical edges. Now, if this is not like if you can see the image, it's like pretty obvious. It is detecting vertical edges very well. Like you can see the edge of the coat over here. It has been detected pretty well by this Sobel kernel. But if you want to see this, like the seating area of this chair, that is like a horizontal edge. So you see, you cannot like identify this horizontal edges clearly. And the same thing applies for the Sobel Y operator. That is, it does a very good job of detecting the horizontal edges. So if you will see over here, the code's vertical edge is not that much highlighted. but you can see the seating area, that is a horizontal edge, is very well highlighted. Now, Sobel operators is meant to be used on a grayscale image, and you can it operates really well on this and gives you a very clear output. I've just done it on a BGR image for your reference. You guys can also play it around and operate it on an HSV type image and see it. So you can see Sobel X, it detects the horizontal edges pretty well, but the output, as you can see, is pretty disastrous. Uh, and same thing, it detects like vertical edges over here. And I mean, if you guys were to see these colors BGR image, so you guys can like see this contrast very clearly. One thing which you could try is input this image in a BGR type and then do the Sobel operator. You'll get a much more clearer understanding. So next up, we'll be using an algorithm that is very commonly used in edge detection, which we call it the canny edge detector. Now, canny edge detector is basically a 5-step process which we do to finally get the edges of an image. First up, we apply a Gaussian blur filter, or what we saw above was the Gaussian blur, to smooth out the image, remove the noise. And next, we find the intensity gradients of the image, that is basically apply Sobel operators. Third is we do something called suppression to get rid of noises around the edges. And fourth and fifth is we apply thresholding and use hysteresis finally to get the definite edges in our image. So what Gaussian blurring or Gaussian filter does is, since there will be a lot of noise in your input image, what we do is we pass it through a Gaussian blur function and reduce it to a low filter or a low frequency image, and that is essentially removing all the noise from the image so that the edge detection can become much more cleaner. And so the Gaussian blur basically makes use of the Gaussian function to do this smoothing of the image or blurring of the image. Now, one example is this is the 5x5 Gaussian blur filter that we use. So you guys can like see this. So one thing is this canny function which we'll be finally using. So that does not implicitly do Gaussian blurring. So on our end, we have to use the Gaussian blur function before we do anything. And next is finding the uh, gradient of the image. So we saw the steps that is applied on the x and y using the gx and gy. So what we have to do finally do is we have to combine them. And as you know, edges are not only vertical or horizontal, they can be in any direction. So to do that, what we do is we compute the edge gradient, that is the square root of gx square plus gy square, or the other method, that is mod of gx plus mod of gy, and then we calculate the edge along with which the gradient, the angle at which the gradient is, or the edge is. So we do that using the basic tan inverse of gy by gx. And one thing in canny edge detection, what we do is we approximate any of these angles to these 4 values particularly, because this is further used in edge suppression. So in edge suppression, what we do is, since as you know, edges of an image are like very well-defined sections, and what happens is when you do finally apply this final Sobel operator and calculate the angle at which the edge is, there might be false edges around those image which you don't want to detect. So to suppress that, what we do is we use a non-maximum suppression, and we basically call this as an edge thinning technique, that is to filter out the false edges. So what we do is, once you have gotten this angle by approximating it in one of these directions, what we do is, say if your angle was 0 degrees, so if A is your true edge and you are reading C as your false edge as well, we come to A, that is the pixel at which this edge is located, and sweep around in the 0 degree direction, that is a completely horizontal scale. And if we see any values that are lesser than this, we'll apply thresholding as well. So I'll explain what thresholding is, but basically if you see values that are lesser than thresholding, the threshold value will basically suppress this false edge t c to a 0 value to remove that from this true edge A. say if you were supposed to have detected a 45-degree, you would be basically running this in the northeast and southwest direction, this with its suppression. Or if you were to read it in a 135-degree, you would do it along this edge. If you were to read it in a 90-degree, you would do it in the vertical direction. And so this is how you do suppression. Now you can see this image is basically, this was the blurred image, and we used the Sobel operator and we got these edges, and then we finally suppressed that to get rid of all the false edges that we had. Like you could see these edges over here, which is false, to get like a final smooth perfect edge over here. And next up we apply thresholding values. Now a linear thresholding is basically you go to a pixel. What you see is if this pixel value is higher than your threshold value, that is basically a particular value which above which you will want that pixel to be. So if the pixel value is higher than that threshold, you take that pixel as it is. If it is lower than the threshold, you reduce it to a 0 and you move on. Now, double thresholding is you have an upper threshold and a lower threshold. So what we do is here there's a three-step process. So if a pixel value is higher than the upper threshold, we mark it as a strong edge pixel. If a pixel value lies between the upper or the lower threshold, we mark it as a weak edge. And if a pixel is below the lower threshold, we suppress it. And usually we recommend that the upper is to lower ratio is maintained between 2:1 or 3:1 for good results. And after we see this double thresholding, we apply hysteresis to accept true edges. So in hysteresis, what we do is the image pixel values that were classified as weak edge pixels, if they are connected, if that pixel value is anywhere around a strong edge pixel, meaning that it is connected to a very strong edge, so that is probably a part of an edge, but it has some noise associated with it, or some uh, or it is very thin, so that it gives this low pixel value. So we take that as a definite edge and consider that as well. But if the weak edge pixel is nowhere around a strong edge pixel, we then we know that it is a false edge and we don't consider that. So here, this is like basically we have applied this canny edge detector on this, and we use the 5x5 Gaussian blur, and all the edge Sobel operations and all were done was basically using a 5x5 kernel. So this is how this final output looks like, and which is a pretty good job of detecting these edges over here. So here as well, the functions that we'll be using for edge detections are the Gaussian blur function and the canny function. So the main function over here is this, the canny edge detector function. So here you have the source parameter, which is the input image in grayscale. Please note that. And min value is the lower threshold, and max value is the upper threshold, which we use in double thresholding. K size is the size of the Sobel operator which you want to use. So here we won't be running Sobel operators separately, because canny edge detector does that implicitly within in the function. So we don't have to do that, and it does using a default kernel size of 3. And L2 gradient is basically a binary value. It's either true or false. So if L2 gradient is true, we use this method for finding the gradient magnitude. If it's false, we basically use this method. Now the default parameter is set to false, meaning we use this method. And so if you guys like want to experiment around, you guys can set it to true and find out what it shows you.
Also, Ashish,
So,
we are running short on time, and maybe wrap it up like quickly. We'll have to switch to the next module.
oh yeah, no, we are done. We just have like tasks up ahead, and we are done with the.
Okay. Yeah. Maybe try to wrap it up quickly.
Yeah. So next up, yeah. So you guys can see this did a pretty good job of detecting these edges over here. So next up, we have two. I had two tasks initially planned for you. So one is basically cartoonifying an image. So it takes it to a 6-step process. So here it basically makes use of convolutional filters. And so I have mentioned the functions that you can use over here. So here I won't be showing you this we need. You guys can run this on your own end and try to find out. I'll be showing you the second mini task, which is a much more interesting one. So this one is basically car detection using something that is known as a Har Cascade classifier. So Har Cascade classifier is basically a pre-trained machine learning algorithm, which was trained using feature detection and edge detection to basically identify objects or faces or shapes and such. So this is basically a pre-trained model which I have imported in this task subfolder in the Har Cascades. So here we'll be using a particular cars, the model that was used to identify cars. So here we'll be basically taking in a video the video is cast.mp4 over here, and we'll be running this R cascade. Now, first what we'll be doing is we'll be reading this video frame by frame. And one thing to notice is R cascade works on grayscale images. So we make use of we convert the images, and then we basically use this function called detect multiscale, which is a function in the R cascade, which is used to detect those objects which you want to detect. And this basically gives you an output of it gives you an array output which will show the region around which the car is. So then we basically use the cv2.rectangle to draw rectangles around the cars in the frames, and then finally show you the frame. Now what I have done is I have outputted this as a video as well, try to make it into a video with the frames, and I've given the code at the end, which you guys can run and try it out. So here, if you guys were to do this, you guys can see that frame by frame it reads and detects cars, and it does a pretty good job at detecting these cars as well. So you guys can test out this. And at the end, what I've done is I've given you a do-it-yourself code, which is basically detecting facial, which is detecting face recognition using R Cascade. So I've basically given you the code and left some spaces for you to fill. So you guys can fill it on your own. You guys can take help from this code that is used to detect cars and try to fill this up. This basically uses your webcam to recognize your face. So feel free to do this, and if you have any doubts, you can put it on the group as such. So this is it from the Opencv side. I hope you guys enjoyed this. So next up, we'll have Nivet taking you through the basics of CNNs.
Archush, can I start right now, or are we
Yeah,
having a
man, I
small
think
break?
start right.
Okay. Yeah, okay.
Anyway, what's up, man? Are you trying to share your screen?
Yeah, can you see my screen?
Uh, no, it's not yet visible.
Oh, yes. Is it visible now?
No, maybe log out and log in again. No?
Yeah, just. Ashish, is my screen visible now, or
No, it's not yet visible. I don't think you're even sharing your screen.
I am sharing my screen? It shows me an option to even stop sharing. I don't know what is wrong.
Maybe Google or Google, do you have that PPT open? Maybe you can share the screen.
Yeah, I have the PPT open. Shall I share the screen?
Yeah,
Yeah,
Gokul,
you
if
should.
possible, you share the Canva screen. Okay, your
Yeah.
Canva link there is.
Just give me
Yeah,
2 minutes. I'll
yeah,
open
sure.
it up and see. Just check if it's visible.
Yeah, it's visible. Nived, go ahead.
Yeah, like whenever you want to like go to a next slide, you can just let me know.
Nived, I suppose you're on mute. If you're trying to speak.
Yeah, sorry, I got disconnected. Sorry. Yeah, Gokul, can you go to the next slide?
Yeah, sure.
Yeah, okay. So yeah, before we go to the first thing about convolutional networks is, so what is the motivation behind convolutional networks? So convolutional networks are majorly used for like image classification or mainly computer vision type problems. So can any of you think of any problems of what would happen if we just used a normal feed forward neural network instead of a convolutional network? You can put it in the chat, or you can just unmute and tell me anything that you can think of. Okay then. So I'll just move on. So the first problem with the first problem with normal neural networks when it comes to this type of problems is that a normal neural network would have way too many parameters for such a task. So a convolutional neural network will be able to reduce the number of parameters. And also another problem is neural networks will not be able to identify the spatial dependencies in an image. So Gopal, if you can go to the next slide. Yeah. So a normal neural network would not be able to identify spatial dependencies in an image. So a spatial dependency is how a pixel is affected by the pixel surrounding. And also a convolutional neural network would also reduce the number of parameters in a model by a drastic amount. So we'll see an example of how this happens later on. So next slide, please. Yeah, so the three major components in a convolutional neural network would first be, of course, the convolutional layers. We'll see how they work. And then pooling layers, which are there so that we can extract useful features and discard irrelevant ones. And then finally, we feed forward that into a normal neural network so that we can classify these images. Yeah, next one. So I guess this part was pretty well covered by Ashish, so we can just skip all this. Next slide, please. So yeah, this is an example of how images are represented. On the left, you have an RGB image. On the right, you have a HSV type. The next one. Yeah, so first, before we feed any image into our model, we perform some certain tasks. So first, our images might be of different sizes. So we resize all the images so that they have the same size. Then we convert images to tensors. We'll see how that is done in our implementation. And then what we do is we normalize our data. So why we normalize our data is because unless you normalize it, certain features might have too much big of a value. So they might like overpower the model in some sense. And also normalizing the data makes the training process much faster. And then during training, we also perform something called batch normalization, which prevents overfitting and also prevents problems like exploding gradient and the vanishing gradient. We'll see how that is done in detail later. Yeah, next slide. Okay, so first, how do we do a convolution operation? So how we do convolution operations by using a kernel. So a kernel is a matrix of weights, and the kernel kind of shifts over the image as we do a convolution operation. A filter is a collection of kernels. So the objective of doing a convolutional operation is to reduce large images into smaller forms. And we also want to kind of detect all the useful features in an image, like edges and colors and all that. So we can go to the next slide. We'll see how to do a convolution operation. Gokul, next slide. Yeah, so how you do a kernel operation is you do an element-wise multiplication. So you take the first element of your image and then multiply it with the corresponding first element of your matrix. And then you sum all of these products, and then that gives you one number, and that's your output. So you can go to the next slide. So yeah, here you have a small video of how this is done. So here we have another parameter called the stride. So a stride is how many pixels you skip over between two kernels. So if you go to the next slide, we can see. Yeah, so here the stride is 2. So here you can see that our convolution operation is skipping 1 pixel between each operation. So, and then what we also should know is the output size of a CNN. So suppose we had a n into n image, and then we perform convolutions with a k into k kernel, which stride is, and there's something called padding, which we'll look into it later. So then the output would be n plus 2p minus k by s plus 1. So we'll see how we get this formula as well. Yeah, next slide. Go. Yeah, just give me just a second. Yeah, sorry. So, we can now see how a convolutional network reduces the number of parameters. So suppose we had an 8 into 8 image with 32 channels in some layer of our model. So that means, and suppose we wanted to have 64 output channels, right? So then our one kernel will be of size 3 into 3 into 32. So that will be our one kernel. And we want 64 such output channels. So we need 64 such kernels. So that convolution layer would have about 18,000 learnable parameters. So we can see that that's already quite a lot. But suppose you had the same thing. So these 8 into 8 into 32. So you would have that many numbers in that layer. So if you had to put it into a normal feed-forward neural network, then what you'll do is you'll flatten this input image. So you'll make this into a list of numbers and then pass it through. So our layer will have like 8 into 8 into 32 inputs, and you want 64 output channels. So you have 6 into 6 into 64 output neurons. So that gives you about 4.7 million parameters. So we can see that CNNs reduce the number of parameters drastically, right? So this allows us to train much faster, and this also allows us to train on larger data sets easily. Yeah, next slide. Yeah, so there's something called padding in neural net when we do a convolution neural network. So there are two things that happen when we perform convolution. So one is, suppose you had an image, and then when you perform a kernel operation, its size would reduce. So when this size reduction happens, this kind of restricts us with the number of layers that you can build. So because after a particular number of layers, you can't perform any more convolutional operations. And also when a kernel passes over an image, if a kernel at the middle of the image, for example, would be covered like much more than a pixel at the edge of the image. So this leads us in a loss of information from the edges. So we don't want that to happen as well. We want to get as much information as we want, and we want we don't want to like be more focused on the central part of the image and not be able to get information from the edges. So we use padding to solve this type of problem. So go to next. Yeah, you can see here that the corner pixel will be covered only once. So this is a 3x3 kernel, and an edge pixel will be covered thrice. But a middle pixel like that one there on the right will be covered 9 times. So you're kind of, I would say, kind of more towards the middle pixels. We are kind of focusing on the central part only. So that would restrict us and will bring down our efficiency. The next slide. So yeah, so in order to prevent this, we do padding. So padding basically means to add an extra layer of pixels to the outer side of the image. So there are primarily 3 types of padding. Sorry for the type there. So first one is valid padding. So it basically means you don't actually do any padding and the model uses only valid data. So that's just the image as it is. And same padding is when we add one extra layer of pixels. So when you do this kind of padding, the output image will have the same size as the input image. So that's the good thing about this. When you do full padding, we cover it with as many pixels as needed so that each pixel is covered the same number of times by the kernel operation. So for a particular image, it might be 2 pixels so that all the pixels in your actual image are kind of in the center portion of your new padded image. So that's called full padding. Go to the next. And then after padding, there is something called pooling layers. So why we apply pooling layers is to reduce the size of the image, and also we want to capture only the important features of an image. We want to kind of reduce the number of features we have. So there are 2 types of pooling. So in pooling, what you basically do is you take a small window in your image and then you perform some kind of operation on it. So if you do a maximum pooling, then you would find the maximum of your values in that window. And if you're doing an average pooling, then you would find the average of those values in that window. So there you can see an image where we are doing both max and average pooling. Here the window size is 2. So when your window size is n, you basically take n into n matrix in your submatrix in your image. Yeah, so that's about pooling. Yeah, next slide. Okay, so batch normalization is actually a very important thing that we do when it comes to convolution neural networks. So you remember that we normalized our data before we passed it into our model. So normalization basically means you subtract the mean from it and divide it by its standard deviation. So now now the data is basically centered around 0. So the mean is 0 and has a standard deviation of 1. But as our model is pretty deep, and as our data passes through the model, you can no longer ensure that this is still true for all the later layers in our model. So this can lead to an exploding gradient or an vanishing gradient problem. And this is called as internal covariate shift. And also when your data is not normalized, what happens is certain gradients might be too large, certain gradients might be too small. So your model will kind of be too unstable, I can say. So yeah, we don't want that because that's not really efficient. So that's called internal covariate shift. And how we solve this is basically by normalizing our data after each layer. So we can go to the next slide. Yeah, so on the right, you have the math behind batch normalization. So you first normalize it as usual. You find its mean, find its standard deviation, and normalize it. And you once again add you multiply it by a parameter and add a parameter. So here now the mean becomes, so on the right you can see the mean becomes beta and the standard deviation becomes gamma. Then this gamma and beta are now parameters that will be learned by the model. So maybe if not for data centered around 0 with standard deviation 1, maybe some other type of data is better for the model. So the model will learn which kind of gamma and beta is best for it, and it will use that. So it increases training efficiency. So another thing is that by doing this, you are adding noise. So this gamma and beta, you are adding noise. So this kind of prevents overfitting in your model. So that's how batch normalization prevents overfitting. Yeah, next slide. And finally, we have ReLU and fully connected layers. So we add a ReLU activation function in CNN so as to introduce nonlinearity. So the first question that might come to your mind is why ReLU, why not sigmoid? So the problem with sigmoid is that it can easily lead to a vanishing gradient problem, because if you look at the sigmoid function, its maximum gradient is just 1/4. So even after like 10 layers, its gradient would be really small, and we are trying to build some pretty deep models here, so we don't use sigmoid that much because of that reason. And then finally, of course, we flatten our output, which means to make it into a flat. We take all our output values and make a list, and then feed it into a fully connected layer and to perform classification tasks. So we look at the implementation using PyTorch. So before that, I want to talk about something else. So next slide. So now our model has like so many layers, right? So I'll be talking about a model called Vgg, where we'll have about 19 layers of neural networks. So what do each of these layers actually learn? So you can think of them like the initial layers learning some small features like edges, corners, and the middle layers, they kind of put together these small features and try to make like small features of the image. So for faces, they might detect like eyes and noses and stuff. And the last layers have like total, they kind of try to recognize the entire object in like different shapes, different positions, different areas in the image as well. So next slide. Yeah, so here you can see how your convolution layers learn. So you can see the initial layers all learning some kind of edges. That's the bottom images in this. And then you can see that the middle layer, they're kind of putting together all of these. Like for faces, you can see they're putting together eyes and noses. For cars, they're kind of putting together the wheels and stuff. So yeah, this is how convolutional layers learn. They start from small features, they try to put them together, and then at the end, they form an entire complete object. Next one. So another thing to look at here is receptive field. So for a particular neuron, what receptive field is, which part of the input does it depend on, does its value depend on? So on the right, you can see the yellow pixel on layer 3. So that basically depends on the entire image. But in layer 2, the green pixel depends on only the small 3x3 matrix. So why does receptive field even matter here? So receptive field matters because they kind of represent the model's ability to learn different objects. So if your receptive field is too small, then like if a particular object is like covering the entire image, then that object would not even be detected. So you kind of try to increase your receptive field as always. So yeah, so how do you increase the receptive field is you add convolutional layers. So you can see that in layer 3, your yellow pixel has a much larger receptive field than your green pixel in layer 2. So adding convolution layers increases the receptive field, and then you increase stride. So if you increase the stride, if you add a stride of 2, then you would be covering almost twice as many pixels as you would cover when you had stride 1. And another possibility is by adding pooling layers. So when you pool, you kind of bringing a kind of merging as many pixels as in your window to form a single pixel. So that increases your receptive field very drastically. Another thing is to do dilated convolutions. So we'll see what dilated convolutions are. Gokul, you can go to the next. Yeah, so this is how your receptive field would change. So subsampling basically means you're pooling layers. So when you do a max pool and average pool, your receptive field will increase a lot. So we'll see what a dilation is. Local next. Yeah, so dilation basically introduces holes in your kernels. So that's like a space between the elements of the kernel. So a dilation of 1 would be just a normal convolutional operation. So on the right, there's a dilation of 2. So when you have a dilation of size say n, then you basically skip n minus 1 pixels between your kernel elements. So you can see that when you do a 3 into 3 kernel, but with dilation 2, we are covering almost twice the number of pixels as you would when you had dilation just 1. So this also increases your receptive field a lot. Yeah, you can go to the next. Yeah, so there have recently been like a lot of CNN based models. So some of them I've listed them here. So one very popular one is called Vgg model. So this model, like there are different versions of this model. Some of them have 11 layers, but today we'll be trying to create something with 19 layers. And yeah, so next slide. Yeah, so one thing about convolution layers or just machine learning in general is when you have a lot of these large models, you have a lot of parameters and you can't train them on your CPU because the CPU is not made for this type of operations. A CPU is kind of made for hard tasks, but a GPU is made for this type of operations where you have a lot of small multiplications, lot of small averaging and stuff to do. So here you use a GPU in order to accelerate your training. So now we'll try to implement the model. Yeah, just Gokul, can you share the collab file that is? Yeah, yeah, okay. So the first thing that uh, the first cell is we're just importing all the required libraries. So next, what I've done is I have calculated the mean and the standard deviation for our data. So so this is just simple, right? So we use this data in order to normalize our model. Yeah, next. So the first line is, so we perform certain operations on our model. So like I said before, we first convert them to a tensor. So that is done by this transforms.to tensor model. And then secondly, we also normalize our data, which is by using this transforms.normalize. So the first three numbers here are the mean of each of the three channels that we have in our image, which is red, green, and blue. So here we are using a CFAR10 model, a CFAR10 data set. So CFAR10 has like 60,000 images of size 32 into 32, right? So they are classified. We need to classify them into 10 classes, like classes like aeroplanes and trucks, automobiles, and stuff. So that's our CFAR10 data set. And we try to normalize it. The first three numbers are the mean of the three channels that we have, and the second three numbers are the standard deviations of the three channels that we have. And then we have our batch size. So we usually take a batch size of like 64 or 32. If you have a batch size that's like 4 or 6, right? The problem is you'll have too many batches and your training time will be too long. So, and then we use, and one good thing about PyTorch is it has certain models in it inbuilt. So you can directly take your CFAR10 dataset out of your PyTorch module. So that's good, right? And then, so the first two lines is torchvision.datasets.cfar10. When you say train equal to true, what it does is it gets the training data. And when you say train equal to false, it gets your testing data. So PyTorch has internally divided the data into like 50,000 images for training and 10,000 images for testing. So you get those in different objects, train dataset and test dataset. And then you create your train set by dividing these images into batches. And how you do it is by using a function called data loader. You set the batch size to your batch size, which is 64 here. And then when you put shuffle equal to true, it shuffles your data. Right? So one thing that you need to make sure in your training data is that your training data should not have too much of just one type of data. So if your training data is composed entirely of aeroplanes, then your model will only be able to identify aeroplanes. So if you then inputted the image of, I don't know, a car, then it won't be able to identify it properly. So you shuffle it well so that you don't end up in that kind of a situation. Next cell. Here. So here we have our VGG19 architecture. So here I've just listed out the number of channels per in each layer, and an M means a max spool layer. Gokul, can you go to the slide of this? No, you can you open the canvas layer of this layer? Add an image. Yeah, the previous layer. Yeah, this one. So here you can see in the 19 weight layers, you can see here Con3 basically means we are performing operations with the 3 into 3 kernel, and 64 means the number of output channels. Okay? But here our input is not a 224 by 224 image, it's a 32 by 32 image. So this I've just listed all of this down in our collab file. Gokul, you can go to the collab. Yeah, so this is basically the entire architecture here, and where M means a max pooling layer. Yeah. So we define a class. I hope you guys are slightly familiar with how classes work. You don't need a lot of it. So here we create our convolutional layers. So Gokul, can you go to the convolutional layers? Scroll down just a little. Yeah, that works. Yeah. So we basically pass in the architecture, and then for each layer, if the layer is an integer type, so 64, 128, 256, or 512, then you create a convolutional layer. So how you do it is by using nn.conv2d. So the first parameter is the number of input channels. Second parameter will be the number of output channels. Then you have the kernel size. Here it is 3. And then we have a stride of 1. And then we have a padding of 1. So when you have a padding of 1, your output image will basically be the same size of your input image for all your convolutional operations. And then after the convolutional operation, you have a batch norm layer, and then you also have a ReLU. What in place equal to true means is it just conducts the ReLU operation in the same matrix, right? So if you had in place equal to false, it would return another matrix, which is another matrix where it has done ReLU, but here it just replaces your existing values after it has done this activation layer. You can scroll down a little bit more. And if your layer is a max pooling layer, which I have represented by M, then you have a max pool. Here our kernel size will be 2 and stride will be 2. So when your kernel size is 2 and stride is 2, your output image would be half from your input image. So if your input image had say n by is of size n by n, then your output image would have size n by 2 and n by 2. And then finally, we do nn.sequential of layers. So in layers, we have added all of these convolutional operations and this max pooling operations, right? So when you finally do this, it creates a model out of all of these layers. nn.sequential would create a model. And then finally so every time you create a class for a model, there needs to be a forward class. So PyTorch would automatically call this function when you call your model. So in your forward method, you would first pass your image through your convolutional layers, and then you perform a max pool. And then once you perform a max pool, you flatten it, right? So you have like, so your image after all of your convolutional operations would actually be just a 1x1 image. So it's just a single pixel, but it would have like 512 channels. So you basically make a array out of all of them, and then you pass them through your fully connected layers, and that will be your final output text. So this is your this is how you create a model. So this is your VGG19 model. Can you scroll down? Yeah. Yeah. So when you're training your model, the first thing is to set a good learning rate. So if your learning rate is too high, then your model will not be able to get to your global minimize. So you need to say, if your learning rate is too high, then your model will kind of be jumping around your loss function. And then you also need to set the number of epochs. So ideally you would set it until until your loss does not decrease at all. But here I've just done it for 10 epochs. And then I've also defined something called device. So PyTorch comes with an inbuilt functionality called CUDA. So CUDA is basically a GPU and you can use it on Google Colab. So if it is available, you set it as CUDA or it is CPU. So you basically pass your model to your device and then you set a loss function. I guess cross entropy loss has already been covered. So this is your loss function would be your cross entropy loss. And optimizer is your Adam optimizer. I guess this has also been covered in a previous class. So Adam, as you all know, is a it's a variable. It uses a different learning rate for all your parameters. So initially we do give it some learning rate to start off with, and then it sets its and then it adapts its the learning rate for each parameter separately. Yeah, so you can scroll down a little bit. Yeah, so now we are training it. So in our training set, we just pass each image through your model, and then you calculate the loss. And then how you do back propagation is basically loss dot backward. So yeah, it's just that simple. And then how you update all the weights is by using optimizer dot step. So your optimizer here is an Adam optimizer. So it will update all of your parameters in the model. So can you scroll down a little bit? Your next selection. Okay. So first we look at what an output looks like from the image. So now out of the testing set, I've taken an image and I've passed it through the model. So here you can see, so what is this torch.max outputs comma dimension equals 1. So outputs will have, so our test set, each image in that would actually be equivalent to 64 images because our batch size was 64. So for each of these 64 images, we are trying to classify it into one of 10 possible outputs, right? So between aeroplanes and cars and trucks and everything. So it would basically give a probability of a particular image being something. So we find out what is the maximum among these outputs. And that is our prediction of whether this is a car or whether this is a truck or whatever. So that would give us, so torch.max, the way it returns its value is by, it gives two tuples as its return. When it returns two tuples. So your first tuple would be the maximum value itself. So, and the second tuple would be at which index did it occur. So we are basically concerned only about the index because the index is how we know what we are predicting. So an index of 0 means a car or index of 1 means a drug. So yeah, that is how, so that is temp and that is spread. So you can scroll down a little. You just, yeah, so you can see. So here I printed out the first values in temp, pred and the label. So we can see that the prediction was 3 and the label is also 3. So basically our model was correct in predicting that this was of a particular type. Yeah, next cell. So now you just do this for the entire testing set and then you find out what the accuracy is. So you get about 82% accuracy on this. I guess the implementation might be a bit fuzzy here and there, but it is actually pretty simple since you're using PyTorch. I guess you should look over this entire thing and ask doubts. And I think this will be fun. Yeah, so do any of you have any doubts in whatever was covered by me? You can just unmute and ask.
Samir, I don't think there are any questions. Is there anything else to cover?
Yeah, I guess this was my topics to cover. Yeah.
Okay, so shall I stop the recording then?
Yeah, sure.